Going live. Hello, world. We're trying to solve some LeetCode today. The topic is binary search, and we have a problem. So, our first task was to pick a problem. I hope I'm sharing it right now. And 786, smallest prime fraction. I like problems with prime. And you are given a sorted integer array. Sorted integer array. Okay, that sounds like binary search already. Containing 1 and prime numbers. Oh, okay, prime numbers. Okay, where all the integers of array are unique. Okay, you're also given an integer k. For every I and j where I less than j, within the indices of the array, we consider the fraction, okay, I divided by j, okay, smaller divided by bigger. We consider the fraction. Return kth smallest fraction considered. Return your answer as an array of integers of size 2, where that's array I and answer 0 array j. Okay, so we need to return those two numbers, kth smallest fraction considered. Okay, let's look at an example. By the way, I forgot to mention, we're trying to solve this within 30 minutes. Okay, we have 1, 2, 3, and 5. And by the way, yes, second example shows it doesn't have to be all the primes in order. It could be just primes. They are sorted, but it could be some missing primes from the prime sequence. We could have return. Okay, so k is 3. And basically, okay, the fractions to be considered in sorted order are okay, because so it's any I, any j, but we're just so I like 1 divided by 5. Okay, so if we want to look at the bigger one, the smaller one would take the smallest one divided by the biggest one, and then and so on. And but here is the thing. So we have 2 pointers. 2 pointers. Yeah, but look at that. Check this out. The next one is the next one is 1 divided by 3. We don't have to write this, but the next one is 2 divided by 5. So it's not 1 divided by 2, it's 2 divided by 5. 2 divided by 5. And then it's 1 divided by 2. So by the way, what this is doing is just getting all the fractions considered. All the fractions. It's getting the well, in this case, we're not doing. Then 3 divided. Why is 1 by 5 smaller? 2 divided by 5 is smaller. So this is essentially 4 divided by 10. Yeah, so this is 5 divided by 10. So it's bigger, yeah. And we need to return what? The third. So like 2 divided by 5. 2 and 5. The third fraction is this. Okay. All right. And okay, some constraints. The values go up to this. The array is up to 1,000 in length, list numbers. Yeah, this one is always 1. Always starts with a 1. Is a prime number. I is a prime number. All the numbers are unique and sorted in strictly increasing order. Unique and strictly increasing. Okay, that's like screaming. Unique scream that screams binary search. K has this constraint of the length. Okay, can you solve the problem with better than n squared time? Okay, because I mean, yeah, n squared would be to create the list of everything, of all the fractions, and then just sort them, and then just get the result. I mean, that uses some memory and some extra. That's well, yeah, that's where the n squared comes from. So now I'm thinking, should I do the n squared solution, because it's pretty simple. It's just list all fractions, sort all fractions, and take return. I could spell return that fraction. Well, we'll have 2 numbers, so we'll just return those numbers. Fraction k fraction, yeah. But that's n squared. I mean, it's gonna run because. So should we try to do the follow up? I guess. I mean, I think for the medium level problem, the follow up option is feels a little bit more up to the level expected. Yeah, my feeling. For some reason, I think so. Yeah. So to do that. Because to get that list, yeah, that's n squared. But can we do better? These are sorted. And so if we want to at least have that list, but once we have it, we're done pretty much. But so how can we do it without having that list? although, yeah, the numbers are sorted, but the fractions, you see there is it goes like smallest left, smallest number, the divisor, dividable, yeah, being dividable, yeah, divider, dividee, divisible, divisor, division, divider. So the left number makes sense to be that one up to some point. At some point, two is even smaller. So, I mean, we wanna try to tell that this number is kth in the list of all the numbers, all the fractions. We need to go over them. My feeling is we can't just say, okay, I think that this is, we can't just guess, like this is, so if we take a guess, we need to be able to prove it. I mean, binary search is guessing. So like, let's try this. And so how can we check that it's third or not? Third, smallest. This is sort of n squared. Let me write a line that's always that's always helpful. So k can go up to n squared. Which suggests, by the way, well, not completely n squared, but sort of, because this is, what is this? This is n minus 1 divided by 2. Well, no, this is n by n minus 1. Yeah, this constants asymptotically, this is n squared, which suggests that we're not gonna iterate all of them. So I was thinking, like, to prove that this is kth, this is third, we actually will have to list them. And if so, then we can't do that for all types of k, also for the k within that range, because this k goes to n squared. Yeah, right, because this is what this is. If we look at that specifically, this is n squared. Okay, yeah, then okay, what is another? Is there another way to tell this is the third one, or this is this one is this n by n minus 1 divided by 2, so which basically is This is a constant. Yeah, this, by the way, this formula looks familiar to me. This reminds me of this reminds me of a number of all possible fractions in this case. Yeah, 1, 2, 3, 4. So it will be like 1. All the pairs, yeah, all the possible pairs. This is probably, it looks like so, yeah. What is, so right now the to solve it with this, a follow-up one, can you solve with better than n squared? Complexity, and they're not even saying time, they're just saying complexity, so both, it's gonna be space and time. So with better than n squared. So both. Because to do that, yeah, how to, do we need to prove, return the kth smallest? My laptop is getting hot. Minute 16. minute 16. Can I just adjust the video? No video settings. No, yeah. So it looks like okay. I feel a little stuck. I feel I got a little stuck. Moment of being stuck. And how to tell this is kth smallest value. Like if we give a fraction, for example, as an array of integers. Okay, yeah, but like in the first example, in this case, by the way, we're guessing with 2 pointers. Yeah, the sorted allows us to kind of, okay, if it's too big, we move the right one. Oh, the left one. Yeah. No. If this is too big, if we want to make it smaller, the only way to make it smaller is to, there's no way to make it small. That's the smallest you can get, like this left and right, this one. So yeah, so that's good to know, by the way. Yeah, so leftist by rightist is smallest number. What's the biggest number you can get? I don't know. Because it always starts with 1. But like 3/5. Okay, and the fact that they're primes is probably also giving us something. Well, that tells us that they're there is no divisor, common divisor other than 1. Yeah, that tells us that. Like 5 by 7 is a pretty big, it's almost 1. But by the way, maximum we can, so the smallest is this, the largest is basically the max, that's min, and the max is trying to become 1. Okay, so you cannot get more than 1. Okay, basically there is a fraction, and it's trying to become, but it never. For example, it could be something like, I don't know, as an example of a, like this, I don't know, like this 17 and 19, right? Or if it was like, I don't know, 93 is not prime, but whatever. If the closer they are, it's like, let's say it's a prime, and let's say this is a prime. Well, this is very close to 1, and gets closer and closer. Yeah. In this particular case, the max one is, we can get the max one by taking the, so 3/5. Well, 2/3 is even bigger, right? Well, probably, but well, you'll have to multiply by this one by 5, or this one by 3. So it's 10 and 9. So this one is in there. So 2/3, it turns out, is the biggest one. But I know I'm trying to find something, some additional hints out of this. There's something about prime. It could be something, yeah, here that suggests something. Because there is no non-primes. Okay. All these fractions, and since they are primes, you cannot like optimize that per fraction anymore. They're all primes. Yeah, simplify. Yeah, I guess that's the word. Yeah, it's as simple as possible. That's all we know. Well, in this case, yeah, the minimum is 1/5, and the maximum is 2/3. And that's, by the way, the minimum we can find, but even to find the maximum is already a game, because 2/3. If there was a 7 here, so like if you compare 2/3 and 5/7, so that would be yeah, so multiply by 5, so 10, 15, and no, by 7. So we need to multiply by 7. So there's like 14, 21, and this is by 3, 1521. Yeah. So this one is even bigger if there was a 7. So you'll need to compare. Oh yeah, even to find the maximum one is a challenge in itself. So there's probably I should use a hint. I'm not seeing any hints. Yeah. So for some reason I feel limited with this. So I got rid of the limitation of you having to like iterate of all the smaller ones. I just said, okay, let's say we don't have to. But then I figured out that the whole thing is some fraction, and yeah, the whole game is within this this by x divided by x and almost 1 within that range. Then minimum is trying to become 0, maximum is trying to become 1. So that's our search space. But it's even more limited. I mean, it's a pretty big search space in terms of fractions. But we're also limited by this. But they want to limit us even further and saying like, can you do so just better? What means just better? Just better. So it could be just a little better. What is better than n squared? So it turns out better than n squared is n log n is better than n squared. And there was another n multiplied by multiplied by square root of n. Timer is already telling me I need to take a break. We are about to hit 30 minutes on this. So these are kind of, I mean, if you want to get something substantially better, n multiplied by square root of n. Yeah, so instead of log n is good. Log n is good. Square root of n is, now to give you an idea, it's a bit worse. Typically, 25 squared 6 5. So that's 25. But if you take log n, it's like 9 something. Yeah. So log so this 2 to the power of 9. Yeah. So it's, so these, but I mean, log n is when you sort something. If we were sorting, but if we are, what that would be like, or, I mean, we could get log n. We could get log n for something else. Like if we were to try this, like one number, and then use binary search to find the other one, then yes. So when we are building our pairs, if we were to take, let's say, 1, and instead of just iteratively going over the rest of the numbers, we will do a binary search among them. By the way, they are sorted. So we know, we don't know the order, no. I mean, well, there is 3 numbers left. I mean, there is 3 fractions we can do, okay? Let's be clear. With 1, there is only 3 fractions. But the problem is, if we take fractions with 1, and then we'll take fractions with 2, they interweave. So it's not like we just take fractions, 3 fractions with 1, and there's 1/5. Yeah, it starts with 1/5, then 1/3, then it's not 1/2, 1/2. I think we're close. I think we're getting close. 30 minutes. We're not gonna do it in 30 minutes, but I think we're close. So this is a good attempt. Attempted. This is a good attempt. Status. Attempt. Yeah. But what does it give us? I mean, if we can at least measure look, because I think I know where we're coming. So look, we're looking, we know what the maximum, what the smallest fraction will be with 2, right? And that will be 2/5. So we're looking at this range of fractions with 1, which is 1, which is like these, this with this like 5/3 and by 2. We can use binary search to find the value that's actually the last value that's smaller. And we'll find out, and that it's 1/3. So out of this, with 1, we know it's, we know that this is okay, this goes in, and this goes in. This doesn't go in the first. So we can count on these 2. Then what happens? We know that this 2/5 is, then goes this 2/5, and we'll use then the binary search over this 2/3, the rest of the 2s, 2/3. Yeah, we only have 2/3. 2/, so we can step, like we have like 2 here. So the sequence, yeah, so like we already got these 2. Then we know we have this. Then we can 2/3 is at the end. I mean, and so on. And so we can make our steps, make bigger steps, basically. Not take bigger steps, not the steps with with the y by 1 fraction. That will include switching between divided value, the divided between 1 and 2, switching back and forth, like until we. So we'll take this here, because you see we take it with 1, 1, 2, 1, 2. Wait a second. Yeah, then we jump to 3, then we jump back to 2. So it will be switching between those rows. And my interim conclusion is that this high acceptance rate came from the brute force solution, that people submitted the brute force. Is there any editorial? Yay, editorial. Yeah, so binary search. And the key is smallest formed by dividing elements of different indices. One to return an array of 2 elements. Numerator and denominator. Okay, these are the numerator. These are the actual math terms. Common denominator, yeah. Denominator and numerator. Vulgar fraction. Denominator below the line. Okay, in Russian it is числитель and знаменатель. Got it. Okay, I wonder how many solutions they got here. Looks like they have a couple of solutions. Priority queue. And by the way, that binary search solution n log m. And they also have the priority queue solution plus k log n. And the binary search solution. What are they doing? What's the intuition here? Okay, for each, I'm trying to understand to count. I was just checking if I had like some viewers, some millions of viewers. Okay, iterate through the array and consider all possible pairs. Okay, for each pair we check if the fraction formed is smaller than the given fraction. If it is, we increment the count. Given fraction. I mean, that's sort of what we're doing in but the given is this is the fraction from the next row. Then all subsequent fractions formed by will also be smaller than the given fraction. Okay, so they're suggesting, like, if you look from the bigger one, like we start with 1/2, numerator, denominator. Yeah, when numerator is 1 and will look like 1/2 is actually still smaller. So everything is smaller if you start here. Smaller than the given is the 2 divided by 5 in this case. Okay, that's true. Then all subsequent, okay, will be smaller. If we apply the above strategy, the fractions formed by dividing elements at different indices in this ordered way will maintain their sorted order. This enables us to efficiently solve the problem using binary search. Now, the key question arises, how can we determine how many fractions are smaller than a given value? We can calculate by comparing their values against a reference value. This reference can be any fraction between 0 and 1, as the array contains only 1 prime numbers. We know that all fractions will be between. Yeah, that's I got. Therefore, we can set the initial search range to, here in 1, we initialize 2 pointers representing the lower and upper bounds of the possible fractions. This looks like partitioning, like, so we just take a pivot and everything that's smaller goes to the left. The interval narrowed down the search space for the k smallest. Okay, let's say, okay, k is we notice that, and all subsequent fractions formed by array k, I, j, k. So they're not talking k. They're talking about where k is bigger. It's just an index. Okay, I got that. We use binary search to literally narrow down the search space for the kth smallest fraction. At each step, we calculate the midpoints. This is a learning video. Okay, learning video. Yeah. At each step, we calculate the midpoint of the range using 2-pointer approach. At each step, the midpoint of the range, mid. We'll compare each element of the array to mid. Keep each element, keep account of how many fractions are smaller than or equal to it. However, while iterating through the array, okay, I don't fully understand this part, but let's go. We're also exploring the set of possible fractions. The smallest fraction first. Why is this maximum fraction significant? In a sorted array of unique numbers, the fractions increase gradually as we move left to right. If we've encountered k or more fractions smaller than or equal to the maximum fraction, and this maximum fraction is the kth smallest fraction. Okay, there is some magic here. We maintain a record of the maximum fraction encountered so far. So far maximum. And they're saying that k or more fractions smaller than or equal generally revealing the smallest fraction first. Fractions for during this record of them. The set of possible fractions. Okay, so we're looking at some fractions. And we're tracking the maximum fraction encountered, we've seen so far. And they're saying that among this bunch of fractions, if we've seen k that are smaller than this fraction, k or more, smaller than or equal to this maximum, then this maximum is the kth smallest. Okay, given we are dealing with a bunch of smallest, and the one that's the biggest one there, for it to be k, we need to have less than k or almost k smaller ones, k minus 1 smaller ones, but finally with just the search range based is the smallest fraction based on the count of smaller fraction. If the count equals k, we return the current maximum fraction as the kth. This is not intuitive for an interview. No. This is not intuitive. This has high acceptance rate, but okay, that's standard. That was my first line. I like it. That also I had at some point. That is this fraction, yeah, makes sense. Now what now do we tell if we like variables to keep track of maximum fractions and indices? Max fraction, total smaller fractions, numerator, denominator index, j, and everything in between. that everything but the kitchen sink that tells me this is not, this follow-up is not interview question I would expect. Yeah. Okay. This is because I mean then look at that. There will be like another loop for I in the range while j is yeah. I wonder what the comments are. I don't know why, but I'm not getting interest today. I see another task to destroy my confidence. I don't know why, but the BFS one is pretty boring, but the hip one is very interesting. BFS. There is a BFS here. The binary search, I mean, they probably meant binary search. It's BFS. Why are you going breadth for search on a table that contains all fractions? Which is min from BFS frontier using prior. Yeah, so I don't think this is an interview material. I mean, this follow-up option. I mean, I think we had some good ideas and might have even come to a solution. This looks like a little bit of like a quick search. Yeah, we partition, then we like so invention of the century. Yeah, not a interview material, but yeah, but I think so. We found this. Yeah, that line is my favorite one. Hang on thing. So this line also. And then I think we were the reference fraction. Yeah, we were looking at this next smaller one. So one of those. Yeah, it got to some pretty complicated scenario, but I mean, at least we were finding some logic. I need some water. Finding some logic that could bring us to a better than n squared solution where we would just step over some piles of fractions. Yeah. So that's where we got within the first 30 minutes or so. But also, yeah, for training, for interview training, I guess this is just an attempt. We can write 2 hours, like an attempt, and it's not realistic in this case to try to solve it, basically. So I didn't know. I mean, I was wondering, like, what I was going sorted the list by acceptance rate, like just wanted to see if the high acceptance rate actually means that this is more like manageable. I mean, yeah, so it looks like it's too easy for too easy of a problem to solve it. N squared with n squared runtime, but then it gets too hard. When something is too hard, we move on to something else. That's kind of the good algorithm. So, good. I would say my takeaways here would be what is good about trying to solve these problems that haven't been like pre-screened, that are not from some recommended list. I would say because the thing is what you see, it's 2 options. It's either, I mean, several. It's too easy or too hard or just right. So as we're trying to prepare for an interview, we don't want to deal with something that's too easy. That's more like a warm-up problem, easy level. Or if something is too hard, like this follow-up, what's the point? Just building the muscle, but building the muscle, yeah. I mean, if you're super confident, you want to feel challenged. Challenged. Yeah, if we want to feel challenged, well, first of all, the problem here is we're not going to practice binary search with this approach. So there was no binary search in the easy version. So, and we want to do that. What is the value of something that's it's too hard? Because this is essentially a hard level, or even more than a hard level problem, I would say. I mean, you might spend, like, to actually solve it, I don't know if like a couple of hours would be enough to actually solve it with this solution. I mean, because you see, we can do 4 30-minute problems, which are the ones we will probably actually see at an interview. So, yeah, I don't know. It's not building confidence. It's not. You're not practicing the key pattern, the binary search here. You are. What's the value? What's the value? Yeah. If you spend like 2 hours and you might solve it or not. If you do solve it in 2 hours, just to kind of do, I guess, train your, like body and mind to stay focused for 2 hours, to do some heavier weights than at an interview. So when you come to an interview, it feels light. Yeah, I wonder what that would be in English. Yeah, so in English, hard in training, easy in battle. Maybe hard in training, easy in battle. If you get, but the thing is, priority, because right now I have a couple of areas like binary search. Binary search. What else? Maybe something else that I could. What else? If you look at the roadmap, this classical roadmap. Yeah, I guess of the primary patterns: arrays, stacks to pointers, sliding window, linked list. And before we get to trees, then trees and graphs, I guess there is quite a lot to do in the graphs. If I could spell graph. Yeah, in the graphs, in the trees, yeah, binary search, trees and graphs, maybe some stacks. Yeah, to do before doing hard level start making sense, because during an interview you might get one of those just one of these classics, just a good stack problem, okay, or good graph problem, good tree problem, and you might want to solve it. You need to solve it well before you try to do some fancy extra curriculum. So extra curriculum. If I could spell extracurriculum, extracurricular, yeah. Extracurricular. I almost spelled extra. I could spell extra. Okay, that's the stream. Thank you for watching, and we'll see you in the next video.